Your desktop cloud drive icon acts exactly like a local directory, but dropping a file inside kicks off massive orchestration across a globally distributed network. This is the standard Google Drive interface, showing a clean list of personal files. Behind this is a rigid technical mandate. Every document, photo, and folder added here must perfectly synchronize to the mobile app on your phone, and vice versa. To understand how this works, we need to focus strictly on state synchronization for file storage. We are mapping out how to reliably store and sync files across devices, ignoring real-time collaborative features like Google Docs. A cloud storage service operates under a primary directive of absolute reliability. A user might forgive a slow upload bar, but permanently losing a single personal file destroys trust in the product permanently. Designing this system requires a quick back-of-the-envelope calculation to understand the physical constraints of our hardware. Let's assume a baseline user metric for a mid-sized global product, 50 million total signups, with 10 million daily active users interacting with the platform. If we grant each user a standard 10 GB free tier, our back-end architecture must immediately support a 500 petabyte physical storage requirement. Those 10 million daily active users are continuously generating data. If they upload an average of 2 500 kilobyte files every single day, the system absorbs an endless, heavy stream of inbound traffic. Procuring enough hard drives for 500 petabytes is a matter of capital. The true engineering bottleneck is network bandwidth. Pushing millions of overlapping file uploads and downloads across the internet will choke standard server connections. Managing raw data volume is secondary. The system design must aggressively optimize network bandwidth to prevent the entire architecture from collapsing during continuous file syncs. A junior engineer's first instinct is a monolithic setup. Route users to a single web server, connect to a local metadata database, and dump files onto an attached hard drive. Under our calculated load, that local hard drive immediately hits its physical limit. Even if you buy the largest enterprise drive available, this single server represents a fatal single point of failure. If the motherboard fries, user data goes offline and the network access drops to zero. Attempting to back up this system by perfectly copying massive monolithic files to secondary servers consumes too much time and bandwidth. The processes are too tightly coupled. As long as the physical file bytes and the file's metadata are bound together on the exact same machine, the architecture cannot safely scale to support millions of users. To achieve true scale, distributed storage architectures execute the great decoupling. The system is sliced horizontally. Above the line is the control plane. Here, stateless API servers rapidly process lightweight metadata, file names, folder structures, user profiles, and access permissions. Below the line sits the data plane. This is where heavy-duty, highly redundant object storage systems handle the massive burden of the raw file bytes. This architecture diagram shows the decoupled upload flow. A load balancer takes the user's request and routes it to an API server. That API server updates the metadata database and cache, completely bypassing the physical file upload. Decoupling allows engineers to scale the metadata databases to handle high web traffic independently of the massive, slow physical storage arrays holding the files. With the metadata handled, the user's device still needs to transfer the actual file bytes. But uploading a raw, monolithic file directly to a cloud bucket wastes bandwidth. We place a specialized microservice directly in front of the cloud storage to act as the heavy lifter. This is the block server. Looking at this flowchart, we see the block server intercepting the user's upload. It chops the incoming monolithic file into uniform cryptographic blocks, typically capped at 4 megabytes each. Before any data hits the cloud storage, the block server independently compresses and encrypts every single 4 megabyte chunk. This chunking process enables delta sync, which aggressively preserves bandwidth when a user edits an existent file. This delta sync diagram illustrates the optimization. If a user modifies one paragraph in a massive document, the system calculates the change and transmits only the newly modified 4 megabyte blocks over the network. The rest of the file is left alone. If two different devices attempt to upload modified blocks for the same file simultaneously, the API server applies a strict conflict resolution rule. It accepts the first block to arrive and flags the second for the user to review. Splitting files into uniform blocks and applying delta sync optimizes the data stream, protecting the network from buckling under millions of daily edits. Once a modified block is safely compressed, encrypted, and stored in the cloud, the system faces one final challenge: alerting the user's other devices to download the update. Referencing the system diagram again, we see the notification service. This is a publisher-subscriber engine that maintains a persistent, long-polling connection with all active clients. As soon as the metadata database logs a new block upload, it triggers the notification service. The service instantly pings the user's other devices over the long-polling connection, instructing them to pull the new blocks. In reality, mobile devices drop off the network constantly. A phone might power down or enter a subway dead zone exactly when an update triggers. To handle this, the system routes pending sync events into an offline backup queue. The queue holds the update instructions safely until the client regains network access and reconnects. Relentless asynchronous event queues push and pull these block updates in the background, guaranteeing eventual consistency across all devices. Moving from a naive single-drive folder to a globally distributed state synchronization engine requires breaking data down to its components. Reliability and speed at this scale demand a strict architectural separation of the control plane managing metadata and the data plane holding the raw file bytes. DeltaSync and block servers operate constantly in the background, ensuring global network bandwidth remains intact by transmitting only the exact bytes that change. System design relies on gracefully managing the tension between consistency, latency, and hardware failure. But chopping files into millions of 4-megabyte chunks introduces a new problem. How do those block servers calculate cryptographic hashes to deduplicate files without melting their own CPUs? We'll map that out in Part 2.